Well, hello, chemists, and welcome to Wednesday. Today we're just going to have a very quick lesson looking at converting between the units that we use to measure pressure in gases. These unit conversions will work out much in the same way that you're used to making your conversion factors, so it should be stuff that you're kind of familiar with, but we're going to show you new units today that we'll use throughout our upcoming unit on gases to define pressure. So, without further ado, here's gases, here's under pressure. I don't know if anyone appreciates that photo, I thought it was funny. and yeah, so here's clouds, here's our atmosphere, and the composition of Earth's air has changed over time. It is currently a homogeneous mixture of these two types of gases, mainly nitrogen and oxygen. Then there's also like some water vapor, carbon dioxide, even some like argon and like some random stuff. But yeah, there you go. So it has all these types of gases mixed together, and people notice that the atmosphere is there. Like we know that we're breathing oxygen. We can tell that when gases travel through the air, and you smell when someone passes gas and you can smell it. So like we know that there's gas surrounding us, and we've known that for a long time. Also, if you think about other atmospheres, like if you think about when you're on the moon, you obviously have less air. Like when you're way on the top of Mount Everest, you have like thinner air and less oxygen. This is all coming to do with these atmospheres. Anyway, all this is today is kind of a segue into some observations that people made historically about pressure. So, Torricelli, this is a name that we're telling you because he has his own unit, invented the barometer. So, you may have heard the word barometer. It's the device that's used to measure pressure, and it measures air pressure by how high the mercury is forced up in the column. And here's just a number you'll have to remember. It'll be given to you in lots of places too, like in your notes and such, but it's the standard height of mercury supported by air pressure at sea level is 760 millimeters. So that means if you just let gas push on mercury, like up into a tube based on you basically just let air in, it's going to exert a pressure going down. That's just like the weight of the air essentially, the, and the pressure that it enacts, and that's going to push the mercury up a tube, and it goes up 7.6 centimeters or 760 millimeters, and that's just right at sea level. Pascal also recognized that height affects atmospheric pressure. So as you go up a mountain, less gas molecules are subject to gravity. So basically the gas molecules getting pulled on less hard when you're further away from Earth's core and like the sea. And that's what causes a lower pressure. There's less pull on the gas molecules, and less pull on these gas molecules means this will be different. The next slide, yeah, this slide is a better photo on kind of what's going on. We have all our air here, and it's just going to push in, push in, push in, and exert a pressure onto like the mercury, or the atmosphere could as well. And yeah, so this is a manometer. It compares the pressure of a gas against the atmosphere by seeing which way the mercury rises. So imagine we have some gas that we're wanting to measure. Let's say like we just put some carbon dioxide in there, and we take just this other end. This is just open to like the room, you can imagine. It's just an open top, but both of them are filled with gas because gas is just surrounding us. And then we can measure things in relation to the atmospheric pressure, which we just define as normal. So one other thing is Gay-Lussac. He recognized the law of combining volumes, which helped kind of aid this chemical understanding of gases, where he noticed that if you put hydrogen and oxygen gas together, you'd get a smaller volume. So two volumes of one hydrogen combined with one volume of oxygen to form two volumes of water. And you can connect this to your whole molar volume thing. You remember how 1 mole of a gas is 22.4 liters? So you're already familiar with that, and that's what we're talking about here. Obviously, when there's less volume, there's also less pressure because there's less things bouncing around and taking up room. So here's a nice little illustration to show what we mean on these manometers. Let's say the gas has a higher pressure than the atmosphere. We can have it be pushing, 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 and it'll push the atmospheric pressure up, and we can measure a height that it goes up. Or if the atmosphere is stronger, it can push the gas up. See, then we can measure like the height that the gas goes up or like the atmosphere side goes down. So you can find the pressure of a gas by determining the atmospheric pressure plus the height, or the atmospheric pressure minus the height. Because you know the atmospheric pressure, we just call it 1 atmosphere. That's a preview. And then based on how hard another gas is pushing, we can define its pressure. Um, all these sides are really showing you right now is how gas actually exerts a force that we call pressure, and it can actually be measured. Um, so yeah, the height of the movement of mercury added or subtracted to the known air pressure to find the pressure of the gas. Here's like the meat and bones here that we need to introduce this week so we can actually start to look more at how gases work moving forward. Notable units of pressure. Down here, you'll see we have these four equivalents. This is like the meat and bones here. These are all pressure units, and these all are just saying the same amount. They're all just saying like normal air around sea level. Um, a Pascal is the standard international unit. That's a fancy way of saying it's the one that scientists mainly use. So that's like things like kilograms and meters, stuff like that. Um, it's defined as 1 Newton of force per meter squared. So if you remember back to like your grade 10 motion and such and force, and you're thinking about newtons, or if you've taken physics, imagine you're just pushing down with 1 Newton of strength on inside a box that's a meter by a meter by a meter by a meter. But we typically are worried about higher, like that's not a very hard push, that's a very, very, very weak push. So we typically use kilopascals, which are 1,000, just like a kilogram, because that's 1,000 newtons per meter squared. Next, we have an atmosphere. This one's simple enough. It's just one atmosphere means the pressure of one one atmosphere at sea level. So it represents the air pressure at sea level, meaning just how much the air around us will push on us. That one's a nice number. Millimeters of mercury. It's historically important, again, not as commonly used today, but that's the whole 760 thing, and measuring the actual movement of mercury up a tube. Then pounds per square inch. You might hear that if you work with like cars or something, and you're like thinking about tires. That's imperial, so we don't use it too much in science. You might see some conversions with it because you do get given it in real life a lot. But it's pounds per square inch, so pounds, inches, imperial. But it's doing a similar thing as newtons per square meter. So it's like a similar unit, just imperial and metric. So these are our four conversions, though. Make sure you write these down or highlight them in your notes, because these are how we're going to do all the problems for today, and what you're going to need to know moving forward when we get into like gas stoichiometry and different like gas laws and stuff. Um, so take a good look at these. One ATM, one atmospheric unit, is equivalent to 760 millimeters of mercury, which equals 101.325 kilopascals, kPa, or 14.7 psi, or pounds per square inch. These are all the exact same number. They're just written in different units. So we're going to do more dimensional analysis here, which is a fancy way of saying conversion factors. We're going to start with what we know, create the conversion factor, put the units we want to cancel on the bottom, and the units we need on top. You would have already seen this in the stoic units. This should not be anything too crazy for you. In fact, these numbers are easier than stoic numbers typically, so bonus. So we're going to multiply and divide. It's like the whole how many pizzas would 200 pieces of pepperoni make. You have 200 pepperoni. Let's say there's 19 per pizza. We can make 13.2 pizzas. Um, Here is the question. I'm going to give you an opportunity to pause the video and try this on your own. Then we're going to pick back up in a few moments here. But basically, set up this PSI thing to find millimeters of mercury or atmospheres using these equivalencies. You can make conversion factors. So I'll give you a moment to attempt these two questions to find the millimeters of mercury and the atmospheres for this. And we'll come back in about 5, 4, 3, 2, and we are back. Cool, so here we're just going to take our 8.5 psi, and to set up our conversion factor, we just have to put what we want on top and what we want to get rid of on the bottom. So we want millimeters of mercury, and that has an equivalence of 760. Want to get rid of psi, so 14.7 has to go on the bottom. Boom, boom. Then we're going to cancel out, and we get left with 440 millimeters of mercury. Awesome. Then 8.5 psi, we want atmosphere. 1 atmosphere will go on top. And underneath, we're going to have the psi. So 1 over 14.7, we get left with 0.58 atmosphere. One thing I will mention here is this 1 atmosphere is like infinite sig figs, so don't think it's only 1 sig fig. But anyways, so these conversions aren't too bad compared to what you've been doing. Honestly, stoichiometry gets a lot more confusing with these whole conversion factors, and you're pros at that at this point. So these work out the same way. For today, there's practice on these that I'd like you to do in your yellow booklet if you still have the booklet. Otherwise, I posted the sheet from the booklet. Um, and then tomorrow, we're going to have a few question quiz on that, along with some stuff about phase changes. And then once we have all that out of the way, we can go on and really dive into gases. So there's lots to look forward to, chemists, and I hope you have a lovely day. Take care.